pointer. Okay, and yeah, there's the time. Perfect, okay. Welcome. I'd like to thank the organizers for giving me this opportunity to speak about the project over here that I did with Rob Klabbers, who's at Humboldt, and Michelangelo Preti, who's between different places, and he's also in the audience today. I'm going to speak later. And this is a project that we started when we were postdocs at Nordita and resulted in a peer-reviewed publication this year. Okay, so let's jump into the business. I'm going to talk about different, sorry? No, nothing. So I'm going to talk about different topics and start a bit from like high energy scattering in massive QFT or QCD, just to set the foundations. It's mostly like textbook knowledge. Then I'm going to connect it to four-dimensional CFTs and Regge theory over there and light ray operators. And it's going to be the two combined together for the Regge spectroscopy of n equals 4 super young mills. That's the main topic of my talk. Okay. Let's talk about scattering. So we are interested in scattering situations when there's like high energy forward scattering, typically elastic, let's say two particle scattering, and we're curious how to describe the behavior of the scattering in this regime. This belongs to the regime when the Mandelstam S is really big, the center of mass and energy mass, and the transfer momentum Mandelstam T is negative. And what we see in experiments that there's like a power law behavior for large S, and understanding this power law behavior theoretically is like an interesting and important question. And to this topic, there was a crucial results from Tullio Regge, who apart from physics, he also did important contribution to furnitures and combined the quartic function to something ergonomic and the chair. But then, back to physics. So this was the time when there was no QCD, no microscopic description of the strong interaction, and people tried to understand scattering through analytic properties. This was like the first era of analytic S-matrix Bootstrap. And what did Regge do? He looked at the scattering amplitude A, put in like a partial wave expansion, and tried to analytically continue in the spin. And what happens if you do analytic continuation? In a way, if you depict it in like a complex spin space, first the partial wave sum can be rewritten as like small contours or integer spins, and then you start modifying the contour. It's not moving. Okay, the pointer died. Did it? It's not jumping, not forward. Okay, a small intermission technicality.
Just a minute, please.
Okay. Then any questions in the meantime for these first few minutes? No. Sorry? I haven't tried, I just found it yesterday, but I think the chair might be really nice. I mean, the furniture company was really proud of it and even had like a description of Regge, like an obituary in their webpage, so I think it's like... Okay, let's see if this works. Yes, it works. And do I have a laser pointer? No. Can I have the laser back from the other one, please? There's no pointer on this one, at least it's written don't press. Okay, then I try to go without pointer in the meantime. Okay, back to business. So, analytic continuation in the spin. Let's start combining these contours. And the more you try to move the whole contour to the left part. And what happens if like you might have other singularities and this contour will be like stuck there. And we're going to pick up a contribution, and this proposition is going to describe the dominant behavior of the amplitude, like this power S alpha t is belonging to the property of this pole. And you can also have like more complicated structure like a branch cut, and there's a bit more corrections to the amplitude's behavior. But still, it really depends on the position of the singularity in the complex spin place. And if you combine this with the optical theorem, you can say that the total cross-section is going to depend like S to the alpha 0 minus 1. And what we should take home from this whole Regge business is that there's this alpha t so-called Regge trajectory that describes the scattering process in this large S regime. And the alpha 0 is called Regge intercept that describes total cross sections. Okay, let's try to understand what does this trajectory really mean, or what the physical interpretation. And this came from Chu and Frauche, who asked the questions like, okay, scattering happens for t negative, but what happens for t positive? And what you see that if your this trajectory for certain t positive values take like integer or maybe half integer, then that's going to be describing like resonant processes in the scattering process. So like actual like physical resonances over there. And like they plotted like meson resonances in this t and spin plane, and they find like there's like a linear sort of like line organizing them. And they said that, okay, then maybe we can say that this Regge trajectory belonging these meson particles is just like a linear curve with a certain like intercept and like a slope. And they hope that they will describe the scattering process in the t negative regime. And that's indeed true. If you put in the scattering data, you see that everything right from this red dotted line are the small resonant measurements, and the left is the scattering, and this linear Regge trajectory is indeed describing scattering. So the take-home message from here that the Regge trajectory is really connected for band states of your theory, and if you can now do some continuation from the particles, you can end up describing the scattering process. Okay, this was easy and nice. Let's see what happens if we bring protons into the business. And there's like a theorem by Isaac Pomeranchuk that the total cross-section between proton-proton and proton-antiproton scattering, the ratio should go to 1 in large S. And this is also true from measurement. They can fit, and there's like the same results from proton and antiproton scattering. And also you see that if you go for large spin, this is going with positive power of the spin as well, positive power of S, sorry, as well. And then you can fit this kind of intercept values, and they're all going to be the same. And this Regge trajectory belonging to this intercept is called the Pomeron trajectory in honor of Pomeranchuk. Okay, thank you. Cool, and yeah, indeed you can see that the intercept is positive. Cool, let's go further. So this is like the dominant dominant trajectory, Regge trajectory in proton scattering, but what can be subleading? And then there was the question that what happens with the difference of the scattering process. If the Pomeron is cancelled out, what is the next leading one? And there was theorized like an Oderon trajectory that was region, but with charge conjugacy odd eigenvalue. And there was like decades of experimental studies to see what's happening. And it seems that like 3 years ago, LHC announced that they see Oderon related behavior, at least like discrepancy in proton, 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 antiproton. However, there's still like all the giants in the field who are still skeptical. So it's still like an open question if there's Oderon or not. And it's quite interesting to understand if theoretically what they should see and maybe put some input over there. Okay, so this was all about like analytic S matrix results and trajectories. But since we have QCD, we can also calculate some kind of perturbative QCD results. And these 4 gentlemen also calculated the Pomeron result from in-weak coupling. That's called the BFKL Pomeron, like summing up like gluon ladders and leading log corrections. And because of that, sometimes the weak coupling intercept is also called like BFKL regime in the nomenclature. But also what's interesting that in this regime, the QCD has like conformal symmetry. Moreover, you can also see some kind of integrable structures, integrable spin chains related to this Regge limit. And you can also produce some kind of Oderon-related solutions in this weak coupling. But going for higher couplings and more strongly interactive QCD, it's non-trivial and theoretically. So we also want to find the different theories where we can say more about these Regge trajectories. Okay, so let's jump into conformal Regge theory. What happens if your theory is conformal? Okay, first of all, we know that in conformal theory there are no masses, no asymptotic states, so what is scattering at all? And this is answered by the conformal Regge theory, but I'm just going to give you the dictionary how to translate the previous massive QFT phrases into conformal Regge theory. But I'm not going to derive this. So first off, when you had like a scattering amplitude in conformal Regge theory, it's going to be what takes the role is like a four operators correlator. And what used to be the Regge limit of large S negative T is going to be taken by the kinematic regime. Oh, yeah, sorry. The kinematic regime, when these four operator insertion are continued in the direction, then they're going to be pairwise sit on each other's light cone. There's going to be new singular behavior and structure in this regime that's going to mimic the Regge behavior of the massive quantum field theory. Okay. What used to be Mandelstam T is going to be played by the scaling dimension in the conformal theory. What used to be what used to be the band states are going to be played by local operators and their scaling dimension. What was the trajectory is going to be the function of the spin depending on the scaling dimension. And what used to be the intercept is going to be the minima of this S delta trajectory that for our situation is going to be at delta equals to 1. And then if you put this together, then also the amplitude's behavior will be described with this kind of expansion from the correlator. When this interesting object appearing in the sum is going to be the so-called light ray operator, that's a really interesting non-local objects describing this Regge physics or like continuation in spin. And there's like really a lot of active research going on, interesting results in the recent years in this field. Okay, so I talked to you about like massive QFT results, conformal Regge theory, but let's go to n equals 4 super Young-Mills as like a framework to do our investigation. So there are three properties that are going to be important for me at the moment in n equals 4. The first is that it's a super conformal field theory, so it's conformal, so conformal Regge theory applies and we can investigate as well. The second is that we have integrability, as all of you know, and that gives us really strong tools to handle the spectrum analytic continuation and give results out of that structure. And then also we have the principle of maximal transcendentality that tells us that the maximal transcendental part of the QCD results can be related to n equals 4 results. So at least not the whole, but a part of QCD can be captured by n equals 4. And in a way, if you combine these properties, then we can, from the first two, in a way, hope that using integrability in the spectrum, we can say something about the light ray operators and their spectrum degeneracy important properties. That could be a nice, interesting input for the Bootstrap community, let's say. And if we combine a bit with maximal transcendentality, maybe we can hope that we can capture some of the quantitative behavior of regions from n equals 4. That's more than the Pomeron. Okay, a tiny bit of nomenclature. I'm going to denote the usual PSU 2,2/4 symmetry and charges by J1, J2, J3, the R symmetry, scaling dimension data, spin, and conformal spin. The local operators can be, the scaling dimension can be increased like this, when gamma is the anomalous dimension, when there's like a expansion in V coupling in the even powers of the coupling G. And then this tau, this is I'm going to call twist in this business. Okay. So what is our strategy? Our strategy is that we're going to fix like a twist, fix the quantum number, the R symmetry charges, the conformal spin, and maybe some other discrete symmetries, let's say parity in the business. And we assume that the local operators with the similar properties for different spin form a Regge trajectory. Then we're going to use quantum spectral curve as an analytic continuation of the spectrum to connect these lines into a trajectory, and then going to the intercept regime to see what happens in the really this BFK regime limit of these operators, and maybe we can learn something about light ray operators or QCD. Okay. Quantum spectral curve, I think you all see and know, and Simon also summarized, so I'm going to skip this slide. And let's talk a bit about what happened before in Regge physics and n equals 4. So there was already a result for the Pomeron trajectory by Gromov, Kavzakov, and corroborators. This is like a twist-2 trajectory, when the operators can be written as like 2z and different number of derivatives on top of it. And what's important for me to take home from this picture is like the V coupling results or what's happening with V-coupling. In V-coupling, we see that there's going to be a diagonal line. This is the twist 2 line, where the local operators live at the integer spins. Also here, there's the protected one. There's the anti-diagonal, that's like belong to the shadow operators, or like this shadow twist. And there's also a horizontal trajectory in this Reggio limit that also sits where the intercept, the crown jewel of this whole business sits. And what's also important that in V-coupling we see that the horizontal and the fixed twist line have like a cusp, in a way signaling that if you introduce coupling, there's like branch points connecting these otherwise separate trajectories into like a finite resolved kind of mixed object. Okay, but like this twist 2 is like really nice, it's related to the Pomeron, but this is like quite a simple object in Equus 4. So you want to go for more into the zoo of trajectories and see what can be still furthermore. So because of this, we're going to jump and try to understand twist 3 trajectories, or at least part of them. Here I plotted the one loop anomalous dimension of local operators that live on the twist 3 trajectories, and also connected them naively into certain Regge trajectories according to the quantum numbers that they belong. That's like the R-symmetry charges, conformal spin, and also parity of the spin as well. So this is the naive picture, but recently it was also studied by Pedro Vieira and collaborators, and they justified that this naive continuation is indeed valid for these twist 3 trajectories. Okay, so there's like a zoo of them, actually infinite many of these trajectories, but we have to pick out at least one to start our investigation. And what guides us that we want to figure out like a trajectory that has the potential to have the highest intercept in this Regge limit, that translate to have like the lowest scaling dimension for one loop. So we pick this blue trajectory, where the local operators can be described with single trace with 3z and number of derivatives. Put around, they have 300 R charge, twist 3, and they also have parity symmetry. So this is the object that we're going to dig in and try to understand analytic continuation. Okay, so what do we see, first of all? We started from local operators and did continuation for different spin, and see something similar to the Pomeron, but still a bit different. What we see that in V-coupling, the horizontal line is at -2, and the twist line is at the twist 3 line. But we also see that there's like a cusp, so there should be some branch points. The natural question is like, what happens if you go on the branch point? What kind of Riemann surface we have and what is connected in this business? Okay, so we went out to plot out the Riemann surface for the first 3 Riemann sheet, and we see the 3 Riemann sheet. Here we can see like the real delta part of these trajectories, these Regge trajectories. This is the first trajectory, and this is when we go to other sheets and go back to real line. This is what we see there. Also, there's like a plethora of branch points. All of them are second order branch points. They also have like a symmetry for real delta and imaginary delta axis. And it's interesting if you focus on these 2 branch points, and you from the top of this picture, that means that in the pictures imaginary delta and real delta, if you go to V-coupling, these branch points start to asymptote the same one value. That means that in V-coupling, these 2 branch points effectively form like a third order surface, mixing 3 Riemann surface and Regge trajectory together. So that's in understanding how these 3 are interested. We go back to the real delta plane and see what happens with these trajectories at small coupling. Okay, so this is what you see. If we went back, this is the zoomed in what's happening with this resolution, and we see that, yeah, these 3 guys are resolved. But what's the new addition to compare the Pomeron? That we see that the horizontal trajectories are degenerate in V-coupling. We always have like 2 trajectories in the horizontal line in these regions as well, and also we expect here, but we didn't continue around all the branch points. But we expect that this kind of like a conserved property for this surface. And then we can also go up and we see the connection to the twist 5 lines, and I'm talking to this operator a bit later. But this is like a degeneracy that we first saw explicitly in this situation, and we want to understand better what does it mean, how is it resolved. So what we did, we tried to do like an analytic solution of the QSC, and went with the ansatz that, okay, the intercept is starts by -2, and then we expand the rest of it in the power of the coupling. How many minutes do I have? 7 minutes. Okay, thank you. Okay, so I want to point out that here we included every power of G, not just the even powers. Like to remind you that in anomalous dimensions for local operators, everything goes with G square. But here to have the maximal kind of freedom to deal with this degeneracy or mixing, we include the linear G terms, and then try to do the whole QSC machinery. And then we solved P functions, Q functions, difference equation that depends on this first order parameter. And then, yeah, went further. We solved this Mellin transform, get Q functions, etc., the whole machinery. But this I1 is still like a free parameter that describes the intercept. And that comes like a new condition that we see that, okay, this function, the solution that have the good asymptotics that we expect, they have still like a square root branch cap in V coupling at the origin. That sort of suggests for us that if we look at the combination of Q times square root of the Zhukovsky parameter plus the Q tilde, the analytic continued with this, then this function is an entire function for all coupling. So if we demand that this combination with our solutions is regular at the origin, that might give us some conditions for this free parameter. And yeah, that's exactly what's happening, combining gluing with this regularity condition, we get, yes, we get this condition for this I1 parameter that has two solutions, I1 plus minus 2. So we exactly see how this degeneracy is resolved in linear G order, and I stress that we find that the linear G dependence is exactly present. That was surprising for us, but in hindsight it's understandable through operator mixing. But it's still like the first appearance explicitly in N=4 calculation for intercept. Okay, so then let's see how does the intercept look from weak coupling to strong coupling. This is the weak coupling where we started, then we can go up to strong coupling, and we match strong coupling perturbative results. And also we can, numerically, the precision let us fit the first few coefficients in this intercept. And also what's interesting that if we let the, we investigate the local territory of the intercept, introduce delta dependence, then the linear G and the cubic G term doesn't depend on this delta scaling dimension, while the G2 curve has like a delta dependence that's exactly the BFKL Pomeroy solution. So somehow the Pomeroy solution appears again in this P3 solution. Okay. Then one more question that we still wanted to see that, okay, we see that other the Riemann surface with other Riemann sheets, the question like what kind of operators belong to that continuation. So then if we go up in this, continue these lines and go to like even spin, we actually can map these anomalous dimensions to operators in the spectrum. And we see that they have the same R-symmetric charge as our leading trajectory. That's expected. We want them to form the Riemann surface. And also, they also parity symmetric, like the leading trajectory. And we only see these two parity symmetric guys in the twist 5 line. So we expect that this kind of degeneracy level stays, that we have two generate, like diagonal in the twist 5, one line in the twist 3, two degeneracy in the horizontal trajectory here. So this kind of conservation of number of lines in the V coupling survive. And also a question like we know that for the leading trajectory, these operators are really simple, like in a simple trace there was like Z to the cube and some derivatives, but how does the local operators look like in 3 level? Maybe there's some insight from that. Unfortunately, they are really ugly. So this is one of these guys. It's lengths for like 5 operators in twist, and like, okay, this is not really insightful from over here. Okay, but then let's see what did we learn so far from this. So we only went for these fixed twist 3 guys, but we saw that the charges that we set out for a trajectory, they are conserved in the Riemann surface. So there's no mixing between different R charges and different conformal spin. Also, we had like extra discrete symmetries, this parity symmetry that was also conserved in this Riemann surface and what we saw. And in general, we can expect that we will have like diagonal twist lines with local operator living on them. There can be degeneracies. Maybe the more we go, the more and more. There the anti-diagonal for the shadow operators, that there's going to be horizontal trajectories with also with degeneracies depending how deep we go in this surface. And we expect that the crossing, there's going to be similar kind of branch points, second order branch points, or multiple of them connecting these Riemann sheets and mixing them in finite coupling. And we also see that there's the linear dependence is there. That complicates a bit our life in terms of like perturbative inversion around these branch points, but it might be still doable. But there's also like a nice connection now that if we can continue G to minus G, maybe in this middle territory, then we can just swap the trajectories and we don't have to really continue around the whole branch point. That's like, can be like a nice shortcut in certain calculation. Okay, so then just to summarize what we did. So we were looking at these three trajectories, or at least one of them, and did the first non-trivial step out of the Pomeron understanding Regge trajectories and their behavior in n equals super Young Mills. We used quantum spectral curve, mapped the Riemann surface, find different Riemann sheets. We found explicit degeneracy of horizontal trajectories in the coupling. We resolved this analytically and also numerically, and we find linear G dependence for the intercept values. And then a bit of an outlook. So there's like still a lot to do. There's still a huge zoo of Regge trajectories, and it would be interesting to go further and understand what's the most general structure, and see Michelangelo's talk for a part of that big understanding. It would be also important to understand that, okay, we just dealt with the spectrum and continuous spectrum, but what happens with actual operators, with light year operators, when there's this degeneracy? How is that resolved in operatorial level? And then also maybe a holy grail later on, that what is the n equals 4 superimage Oderon, and what is its intercept? How does it depend on coupling? How many Oderon there are, and so on. And with that, thank you for your attention.
Thank you. You have questions?
So given all the lectures from the last week and so on, do you see any mechanism which would allow to obtain linear term in G from perturbation theory which goes in G squared?
I think if you have like a mixing of the operators, I think it's quite natural that you get a linear term. Maybe the operators by themselves have like G squared dependence, but then the mixing will introduce G dependence. I think it's plausible. It sounds like the Bootstrap people find it like natural. For me, it was surprising, but I don't see the actual details how to make it happen in that calculation.
More questions? Well, if not, let's thank Istvan for a very clear talk.
Thank you.